Assalamu alaikum wa rahmatullah. Welcome everyone to Quality Control. Today is a new chapter, very simple chapter. At the same time, it is important. And in the practical life, we need it when we apply Six Sigma project, or even when we use the control chart. It is preferred to use today's tool before we start conducting the control chart. The chapter is about the process capability. What is the process capability and where it falls in the quality? It is one of the SPC tools. It is similar to the control chart, and today we will clarify what is the difference between the process capability and the control chart. Looking to the name itself, the capability, even when we say a person is capable to perform a task, that means his ability to perform such thing. It is similar when we conduct this tool in the process. The definition here is a scientific definition. I would rather to explain the idea with the simple words, and then we go to the definitions. The voice is clear, just to check. Okay. The process capability is the uniformity of the process, how the process is uniformed. Someone we may ask, okay, what about the control chart also looks for the variability and how the process is uniform? I say, yeah, that's true. But the difference is, what is our reference for uniformity when we use the control chart versus the use of the process capability? The process capability and the control chart, they have something in common about the variability. And here it talks again about the source of the variability. We have two different sources of variability in every process. The first one is the natural variability, and they refer to that one is the natural tolerance. It is in the critical to quality characteristics, and this variability usually comes between samples in a short term. Whereas the second type of the variability is the variability that comes over the long time, and you can see it in drifting in the control chart or variation in a wide range exceeding the tolerance or the natural limits. The natural limits has been identified earlier to be the natural tolerance limits. They refer to them as a LNTL, lower natural tolerance limit, and UNTL, the upper natural tolerance limit, and those are usually 3 standard deviations from the mean on the two sides of the bell shape. These considered to be a natural variation, and it happens in every process, and that's why as you can see in the control chart, it is common to use the 3 sigma level or the 3 standard deviation, regardless how the standard deviation is estimated or calculated, but it is about a natural variation. And that leads us to, okay, then what is the process capability has something different compared to the control chart? We demonstrate here the difference between them. The difference between the control chart and the process capability, first, even in the way how they are presented. The process control or the control chart, they look to the process data over the time, and they check the voice of the process. What is the voice of the process? Means that the process natural variation, how it is in the process performed. It shows the process performance and how it is distributed among the agreed performance measured. On the other hand, the process capability, it looks on the voice of the customer. You remember when we talked in the Six Sigma about the defect earlier, we talked about it has to be identified based on the customer and the process owner or the stakeholders, all of them. In the control chart, we don't do that. We have a data. We put this data based on the criteria of the data. It's a variable or continuous. It's a variable or attribute. If it is a variable, then we use the X bar or X bar R or S chart. If it's attribute, then we use the P chart or S chart or U chart. And for those charts, we don't refer or we don't consider the voice of the customer. We look only to the variation with the acceptable performance based on the formula for each type of the control chart we have studied in chapter 6 and 7. The process capability, it considers both the voice of the process, which is the one that is looked on during the control chart, and the voice of the customer. The voice of the customer considered to be the specification here. The specification is not formed based on the measured data. The specification is measured based on the customer's needs and the process owners or the organization themselves. For example, your specifications for a service, it may be different than person to another person. Your specification for the car you would like to purchase is different from one person to another person. But how is the production for a specific car and how is the variability in that production line? This is something else. This is where we apply the control chart and make sure the variation is within control. Whereas the specification is something that be above or beyond the control limits. Because the process, if every time a unit or a product or a service transaction is exceeding the control limits, is exceeding the specification, that means you are going to perform in very low quality level and you will have many complaints in your service or your productions. That's why when you look to those charts here below in this slide, you will see the natural tolerance, which is considered to be the one that is agreed to be normal in any process, is beyond the, here when we start from the left, you see it is beyond the specification limits. So your regular or your ideal case, when you have something like that, your natural tolerance, which means that the 3 standard deviation, which is normal to have them in the process, they have to be beyond. That means it is narrower than the specification limits. So when you exceed your natural tolerance, you are not exceeding the specification limit. This is the ideal case. Here, on the other hand, on the right side is the worst case. When you have your natural tolerance is wider than the specification. That means every time your regular performance is not meeting the specification that is set by the customer. The one in the middle, it is acceptable, but it is critical at the same time. You have to be aware. That means any out of natural tolerance, that means out of the 3 standard deviation, is out of the specification. Why? Because they are both matched at the same place. On the right side, the natural tolerance is above the specification. So definitely you will exceed the specification limits due to the natural variation. Now, what about the control limits? Because the control limits is slightly narrower than the natural tolerance. The control limit is slightly narrower than the natural control limits or the natural limits. And therefore, it has to be similar to this figure where the control limit, it is even narrower than the natural tolerance, and it is narrower than the specification to perform an acceptable quality level based on the customer point of view. In this chart, it shows us how is the relation between the control limits, which we used to do in the control chart on the blue font here, and the red dash is the specification that is set by the customer. Usually, to have acceptable production or service, your specification has to be above the control limits. You remember we had many times points exceeding out of control limits, or even if they are not exceeding, they may have out of control cases that is based on the 8 rules or the 4 rules that we have covered. Imagine if that every time you have out of control point, that's mean you are out of the specification. That's mean a chances to have dissatisfaction or customers that are not satisfied are very high. That's why they refer to the process control as the voice of the process. The voice of the process referring to the control limits, and voice of the customer is the specification limit, and the specification put in the design and the control in the process. What is the difference? The design is set by the designers, by the engineers, and the process is by the statistical tools that based on the data you are collected. You have no influence on the control limits. Is based on how your process is being performed. But the specification, you set them up as a process owner after collecting the voice of the customer. So there is a difference between the control limits and the specification limits. The specification should be wider because it is the voice of the customer and the voice of the process. That's why they referred to the process capability as the measure for goodness of the process. The good, how the process is good, how the process is capable. Recall that example. This person, he is capable to do such exercise. This engineer, he is capable to do such design. That means he has good skills enough to perform that task. Whereas the process control shows the process, how it is performing based on the calculations for the formula of the control chart. How is the variation of the exist process, of the process performance over time, how it is stable and how it is performed. So where do we need the process capability, and why do we need these inferences, and why do we need this explanation or identification in the process? We need them to make sure before we start do the control charts, whether our process is capable to do and meet the specification. If it is not capable to do it, then the control charts has no meaning that time to do it. If you are going to do the control chart and you are not meeting your specifications, what is the point then? You will measure a variation and you may see the process is in control, as you can see on the right side here of this picture. But every time this side here in the normal distribution and the other side, they are exceeding the specification. That means the level of goodness of your process is not meeting the expectation. Those points here, the 7 points, can summarize some of the use for the process capability. The process capability helps you to predict how the process is well, how it can hold the tolerance. The tolerance, which is the natural tolerance. So if it is meeting the specification or it is good enough to meet the specification, then the natural tolerance will be manageable and it will be acceptable. Also, it will help the designer to select the process specification and the process modification needed. Also help you to establish the interval between the sample when you monitor the process. If there is a shift in the process, if there is variation, it will tell you ahead of time before you conduct the control chart about this information, so you can plan your sample size or sample plan. Also, it helps to set the requirement for the equipment to meet your specification. You may rely on a specific specific features for the equipments that help you to perform and meet the specification. Give you an example. Your specification is to process the food within 5 minutes of the order, okay? If you don't have enough equipment or well-trained staff and optimized process, you may not be able to maintain this specification or this time. If you look to the fast food industry, I'm going to give some names like McDonald's, Burger King, Kentucky. Those fast food industry, they have specified equipment and machines, how they store the food, how they can process the food very quickly. And I referred to a movie, I talked about it earlier, about the story of McDonald's and how they speed up the process and how they reduce the time for processing the food in a way that to meet the customer requirement by reducing the waiting time. To do so, when you know what is the process capability and you know what is the specification, then you can set what is the requirement for the new equipment needed. So you can know what type of equipment you need to process the food on the 5 minutes limit. Also, to select between suppliers and know each supplier's specification also will reduce the variability in the manufacturing process. All these are use of the process capability. What is the reason of having poor process capability? When we can say there is poor of goodness for performing that process, we have two incidents or two cases when we have a poor process capability. The first one, if we have off-centering. Off-centering means the process is not centered. That means the distance between the sides of the center of the process is close to or exceeding the specification limits. And the other case, when we have excess process variability. That means the process variability is wide. As you can see, the normal distribution here, it's wider than this one, and it is also exceeding the specification limits, even though it is centered. يعني it's similar, we didn't calculate it, but it is, looks here, it is centered, but the variation or the variability is very high compared to this one. Here the variability is not high, but as you can see, the mu for the process is away from the center of the specifications, and that they call it off-centering. So these are the two cases or the two reasons of poor process capability. What are those process capability parameters, how we calculate them, how we identify them, how we can find them in our analysis or in our data. The process capability are ratios. Ratios mean they are index numbers, and those ratios are categorized in two terms: the capability or the performance. The capability, they refer to the ratio as a C, stands for capability, or P for the performance stands for, the P stands for performance. We have 4 different process capability ratios. The process capability ratios for the capability analysis called CP and CPK, whereas for the performance they call it PP and PPK. Those the parameters need to be calculated to identify the process capability when we use the performance ratios and when we use the capability ratios. The performance ratios are not commonly used because it's used when you have a long-term case and you have a process that is not in control and you have the total population standard deviation. And this is really rare to be implemented or to be used. And the meaning of the long term, if you look to the chart here in the control or the run chart, that means during all the period of time that where you do your study. Whereas the short term of the capability, that's mean in the difference between samples than or a sample to another sample within inside the time frame, not overall the time frame. And also it's considered that when the process is in control and you don't have to have the population in all of the data, the pooled or sample, it is enough. So any case of those 3, you can use the capability, and that's why is the most common to be used compared to the performance index. Now, there are, as you can tell, there is a CP and PP, and there is CPK and PPK. The difference between the first row and the second row is the P here refer to the variability, and the CPK refer to the centering of the process. Remember, the poor process capability or the reason of the poor process capability is the centering here and the process variability here. This is exactly what those ratios do. How the process is centered, the PK do identify how the process is centered. And to identify how wide is the variability and how it is the variability in the process, we use the P indicator. The specification range tolerance to the process width is the variability, and how close the process center is to the nearest specification limits, they call it how is the process centered. So those are the ratios that we need to calculate to identify the process capability. The process not in control when common causes and special causes acting, and this is being already covered in the control chart. And the process is in control only when common cause is acting, no sudden drift or shifts in the process. And this is exactly what we covered, those possible drifts or shift when the points of Western Electric or the Nelson 14 points about the out of control is being covered. And this is when the process only have a common causes, no special causes. How we calculate those ratios and how we interpret the result after we calculate it. Before we go to the calculation, here is the difference between, we talked about the CP and the CPK as one for the variability and the CPK is the one for the centering. Let's see how they look in figures. Imagine if we have a high CP, and the high CP considered to be when we have a value of 2. And this is when we have a high CP case, and the CPK considered to be low as 0. You have a nice variability. That means your variability is not high, but our centering is away from the center line of the specification, because the center line is here at 50, and here the process centered looks like at 60. So it is off centering here, even though the variability is low. But when we have both CP and CPK are high, as in this picture here, we have the process is centered as well as the variability is low. So here, the CP, when it's only itself, is high, the variability is low, but since the CPK, it is low, so the process is off-centering. But when we have the CP and the CPK high, that means the process is centered and at the same time has low variability. Therefore, the CP by itself does not consider to be the process is capable, but consider there is a potential for the capability, but is not actually capable. So when we calculate the ratio, as we will see in the examples coming, that means if you have a CP only high and you don't have a high CPK, then we cannot say that the process is capable. It has a potential for capability, but is not capable. Why? Imagine if you are performing at this level. That means your natural tolerance, which is on the right side of the normal distribution here, it will be above the specification limits, and that means is not acceptable. It will go back here, referring to the poor of process capability. So we need to have them both high. And here is another example, maybe shows you the explanation in a different way. We have a CPK high in here. For example, the CP is decreasing from 2 to 1.6 to 1.3 until 1. And the CPK is also decreasing. What we can see here, when we have a CP high, the highest is 2 for both of them, and we will talk about the threshold and each number, what it represents. But consider now we have a CP is the highest and CPK is at 1, which is considered to be in the middle. We have a good distribution or good variation, is not high, but the CPK, since it is high, it is low, it is off centering. But if we have the CP and the CPK high, we will have something similar to that, where it is centered and the variation is low. The last example here in the blue distribution, it shows when the CP is low and the CPK is low. The process is off-centering because the center is here, and the center for the distribution looks how it is shifted, as well as the variation. You see how the distribution is being wider compared to the yellow distribution. That's because the CP is reduced, and that means the indication of high variability is there. So the process also is not capable. There is a relation between the CPK value and the sigma level, as it shows here in the table. So this is one of the way, in addition to the DPMO, to identify the sigma level. So the 6 sigma level considered to be when the CPK is 2, but at the same time, you have to consider also both the DPMO and the CPK. Specialists consider the DPMO to be calculated to identify the sigma level over the CPK, but both of them are acceptable and applicable. So that's why we said the highest value for the CPK is 2. And we will come to the acceptable and low and a high value for each ratio in a few, but let's know how we calculate them first, and then we see how we interpret their values. Their calculation for the process capability for the performance is here, given the difference in the specification limits divided by the 6 standard deviation, and the process capability ratio also the same. The only difference between those two formula is the standard deviation. In the process capability ratio, the CP and the CPK is estimated, whereas the standard deviation for the process performance ratio is for the overall data. So you don't have sample, you have the whole population. That's why it is rarely to be used, because most of the cases we deal with samples, and in this case, the CP, it will be the one used because it used the estimated standard deviation. To find the estimated standard deviation, you can refer to the formula that we have covered earlier in chapter 6, which is R bar divided by D2, and D2 can be identified from the constant table based on the sample size. This is referring to or regarding the CP. Now let's go to the CPK. How we calculate the CPK? It is the minimum value of the CP, the upper and the lower process capability. The lower and the upper process capability. How we calculate the lower and the upper process capability? In the lower process capability, referring to the CPKL, is equal to X minus LCL divided by the 3 standard deviation. And the upper process capability is the upper specification limit minus the X divided by the 3 standard deviation. Now, is the same for the performance capability PK. And after you calculate the lower CPK and the upper CPK, when you find the CPK is the minimum out of them, and we will see that inshallah now in the examples. This is to summarize the formula. This table shows how you calculate the CP. When it says the CPU, that means the CP upper, and the CPL is the CP lower. The X here means the average, is the X bar, sorry if it is not written here, but referring to the average, because we are not dealing with each data, we are dealing with the average and specification limit. It is a single value divided by the estimated standard deviation times 3. And the CPK is the minimum value of the CPU and the CPL. We will see an example here. This is an example, and it shows how the value is calculated. The example here has an upper specification limits given at 1 microns, and lower specification limit is 2 microns. The R chart was estimated the standard deviation as 0.139. So the CP considered to be the difference in the specification limits divided by the estimated standard deviation times 6, and that is equal 1.192. So this is the process capability CP ratio. How we interpret these values, let's go to the, what is the, let me show you, there is a slide is missing here, or a figure is missing about the value. Let me show it to you in a separate here, and we go back. Hold on a second. Okay, so let's go back. This was not shown in the previous file due to the formatting issue. So when we calculated the value of the CP and the CPK, how we interpret whether this is acceptable or it is poor or it is high and good. This will help you, the figure here. The red means that is unacceptable and the process is not capable. The yellow means the process is okay, but improvement definitely is needed, but it still is capable. The green one, that means the process is very good and performing in a good level. How we identify the value? We calculate the value of the process capability, whether for the process or for the performance, the CP or the PP. And also we calculate the process for the centering for both the capability or the performance, the CPK and the PPK, based on the formula that we have showed earlier. When we get the value of the CP, if it is less than 1.33, that is not acceptable for the CP, and the CPK, if it is less than 1, that is not acceptable. For the process, if it says that, we can say it is okay if the CP value is 1.33 to 1.67, and if the value of the CPK is 1 or from 1 to 1.33, any value from this range considered to be process capable. But as we said, we have to have both of them to say the process is capable, and especially for the CPK, because this is the identification for the process capability. It is rarely to find, or it is always, we can say that the CPK, when it is high, the CP will be low like that, because the value acceptable for the CP, it is easier to maintain compared to the CPK, since this is dealing with a variation and this is dealing with the shifts of the centering. But the process is acceptable when you have both of them are on this range. Both of them has to be in this range. Commonly, you will see in the most cases, when this one here is in this range, you will have the CP also in acceptable value. But you may face one of them is in the acceptable range and one is in the not acceptable range. And this case, you will say the process has a potential for capability, but is not capable due to what? If this one is the one not meeting the requirements, then due to the high variability. If this the one was not meeting the requirement, you say due to the off centering of the process. Now, the case is when we have CPK greater than 1.33 or CP is greater than 1.67, that means the process is capable and it is performing good. Okay, so let's go to our example again and see what we will interpret or what we will refer to our process here. We have the CP value found to be 1.198. Let's go again to the slide. 1.19, that means it is less than the 1.3. So the process is not capable based on the variability. And if you calculate the CPK, you may also find it is not capable for the centering. So the process is not capable. Let's take more examples to have more clarification. Here is the example. The example says a food served at a restaurant should be between 39 Celsius and 49 when it is delivered to the customer. The process used to keep the food and the correct temperature has a process standard of 2 Celsius degree and the mean value is 40. What is the process capability ratio of this process? What will be the upper specification in this case? So the upper specification is the 49 and the lower specification is 39. The standard deviation is given as 2 degrees Celsius and the mean given as 40. Now we go and use the formulas to calculate the CP and the CPK. To calculate the CP is easy to get the difference in the specification limits divided by the 6 standard deviation. So you get the subtraction 49 minus 39, that's 10, divided by the standard deviation times 6. The standard deviation times 6 is 12. So you divide the 10 divided by 12. And that will give you the CP. But to calculate the CPK, we need to calculate first the CPKU, the upper, and the CPK lower. And to calculate that, to do it, we follow the formula as shown here. The CPU, the upper CPK, the upper process capability, is the upper specification limit minus the mean divided by the 3 standard deviation. The upper specification is the 49 degree minus the mean, which is given the 40, divided by the 3 times the standard deviation, which was given as 2, and that gives us 1.5. The CPL, we will do the same, but it is for the lower specification, and the lower specification in the problem was 39 degree. So we apply it, and it is 0.166. So the CPK is the minimum of those two values. So we have to look to this value here and this value here and select the minimum. Which one is the minimum? It's clearly this one. So 0.16 considered to be the CPK. And the CP, as we said earlier, it is easy. It is just 10 divided by 12. The 6 is the 6th standard deviation, and 2 is the standard deviation. Sorry, the 6 is from the formula, and the standard deviation is equal to 2. The 49 and 39, those the upper and lower specification limits, and it is 0.833. In this case, let's refer again to our figure here. You will see both of the values are less than the acceptable range. So what we can say about this process, we will say that the process capability is not acceptable, and the process is not capable. So the process is not capable to meet the specification limits. This is similar to the first example we said, whether this person is capable to perform tasks, or whether this car is capable to drive 300 kilometers per hour. So this process is not capable to meet the specification of the food temperature between 49 and 39 within this given mean and standard deviation. So the process needs to be reworked again. Let's take a Minitab. This is a given data. You can estimate the standard deviation by calculating the R bar as we did in chapter 6, and the X bar also as we did previously. Or also you can just go to the Minitab and calculate the process capability. Automatically will be calculated using the Minitab. I will share the screen now to show you how we do that. Okay, now let's go to the Minitab here. This is the data, and those are the samples. We have 5. The sample size is 5, and we have 20 samples. To find the process capability is very easy. You just go to Stat, and then you go to Quality Tools, and then you go to Capability Analysis. Let's do the Minitab now, and we will go back to the question. So we will do the process capability using the Minitab, using the capability analysis and the normal capability analysis. When you press on that one, is you select the data based on the subgroup of a crossrow. That means you have the data divided for every sample. You have the sample size readings in every row. If you recall previously, you can show all these data in one column, but you have to code the sample size, and you have to identify every reading for which sample size. Is it for sample size 1 or sample size 2, sample 1 or sample 2 or sample 3. But if you have demonstrated the data here as showing row by row, then you can select the subgroup across the row. That means the subgroup, all of them are in one row. and then you enter the data by double clicking on each one of them, and then you put the specification limits, here the lower and here is the higher. You type the specification based on the requirement in the question. When you press OK, the Minitab will calculate all the process capability ratios for you, the CP and the CPK and the CP lower and the CP upper. In this case, also we have all the values below the acceptable range. So we will say the process is not capable. And obviously you can tell from just looking to the distribution here, this should be inside the specification. All these data or all these products are above the specification, and all these product or service transactions are below the specification. Also, it calculates to you the standard deviation for the data, as well as for the PP and the PPK. But as we said, our reference here, or our case, since we are using sample size, we are not using the population, then we focus on the CP and the CPK and refer to the values to our figure there to interpret whether the process is capable or no. So that was for the process capability. And let's go now for the questions in the remaining time.